This is a problem from the practice exam that I had some questions about. So I've drawn a picture of what's going on here on the left. So we're told that a tether ball is tied to a string and hangs at this angle theta with respect to the vertical. We're also told that it's moving in a circle. So as you're looking at it, the ball is moving in and out of the plane of the paper or the computer screen or whatever. That is to say, it's coming towards you or moving away from you right now. So it's connected by the string, and it's moving around the pole. So to the right, I've drawn the free body diagram of the ball. Of course, we have gravity, mg, and then whatever's touching it, the tension, and I've also included the angle theta that it makes here. I believe in one of the emails I've gotten in my solution, I believe I put theta in the wrong place on my free body diagram. The process should be correct, but this gives you a little bit more correct solution. Apologies about that. I was in a super big hurry while I was doing your test. But this is the way the problem is stated. So of course you can do it with the angle. That is to say, I did my solution online, I did it with the angle here. Of course you don't have to do it with that angle or this angle. As long as you have a triangle you can solve, you can do whatever angle you want to. But I'll do it like this, since this is what we've been given in the problem statement. So the first thing I'm going to do is I'm going to resolve some vectors and sum them up. I'm going to resolve some force vectors and sum them up. So I need to find the tension. First of all, I know what M is, I know what G is. I don't know what the tension is, but I'm going to need to find it. So to do that, I'm going to look in the y direction. I'm going to look in the y direction because I have a component of tension in the y direction, and I have the weight of the ball in the y direction. And I know one of those, which means I can get the other one. Sum in the y direction is equal to m a sub y. But if you notice, if this ball is coming in and out of the page or in and out of the computer screen, it's not moving up and down at all. So this is actually 0. We're in equilibrium in that direction. So then I get t minus mg is equal to 0, which of course means, the component of tension, right? Let me change to a different color. The component of tension in the y direction looks like this. That is t cosine theta. Cosine, because with the angle where it is, this is the adjacent side to that angle, right? And that's, if I move this vector over here, I have the component. Let me get rid of all that stuff, but it's cosine theta. T cosine theta minus mg is equal to 0. So of course, t, then, we go to the next page, t is equal to mg divided by, it looks like a y, cosine of theta. Make sure I got that right. T cosine theta is equal to mg, which means t is equal to mg divided by cosine theta. Right. So that's actually not what I'm being asked to find the speed of the ball. So remember, this thing is moving around in a circle. That is to say, it's being accelerated centripetally, right? So I have to have some sort of force in the centripetal direction to accelerate this ball centripetally. Let me change colors again. And if I look, the only candidate I have is the component of tension that looks like this. The component of tension in the centripetal direction. As I'm looking at it, it looks like it's the x direction. Remember, this is moving in a circle, so I'm going to call it the centripetal direction. That is t sine theta. Theta is the angle here. So this side is t sine theta, and I know what t is, and I know what theta is. So now I have it. Let me go to the next page. Let me do that. Sum of the forces in the centripetal direction is equal to m a centripetal. The only force I have in that direction, again, the only thing I have, gravity's all up and down. The only thing is t sine theta. T sine theta. That's equal to m times a centripetal, right? Which is v squared over r. There is a sign convention here I should mention. We usually define towards the inside of the circle as negative. That is to say, this is your center of rotation over here, so this direction we usually define as negative. Notice that's the direction of the acceleration, because it's always centripetal. It's to the center. It's also the direction of the force here. So if I'm going to be really explicit, I would put a negative here and a negative here. But as you can see, those are going to cancel, so I'm not going to worry about it too much, rather apart from just saying that towards the center of the circle we define as negative. But at this point I have it. I can solve this for v. If I cancel the negative signs, I get that v is equal to, what is that, r over m t sine of theta. Let me go to my next page and plug in what my t is, which is mg over cosine theta. Let me go back over here. Oh, I'm sorry, that should be under a radical because it's v squared. So let me rewrite this. V is equal to r over m times t sine theta, but t is mg over cosine theta, and then I have a sine theta, and then that's all under a radical. This is t, right? Let me make sure I copied that down correctly. R over m times t, which is mg over cosine theta, times the sine of theta. It looks like I got it. My m's are going to cancel. I get that v is equal to the square root of r g. Sine over cosine is the tangent. At that point, I plug it in and solve.